Well, we're now going to start our next session, which is looking at new horizons and how we can be incorporating new science and technology with the foundational models. And we're very grateful and pleased to have Dr. Bradley Doorn joining us, who's a program manager with the NASA Water Resources and Agriculture Division. And he's going to open the discussion looking at leveraging satellite and aerial data for climate smart agriculture. Brad, I'm going to release the screen so you can come on.
Hi, everybody. Hi, Cynthia. Congratulations. I'll add it to everybody else's. My name is Brad Doorn, and I am the program manager for applied research. And I'm going to emphasize this. This is going to be a little bit of a theme. I'm going to start off by saying I love the title of this workshop, and I'm going to steal it. We're going to have water, water resources, making water resources work, making agriculture, productivity work. So thank you so much. But the trouble is that I want to maybe draw some threads through my presentation, and so I'm going to start with some standard graphics, and I hope you can see my graphics now.
Yeah.
Okay, great. And so this is on behalf of me and my deputy Sarah Brennan, and I'm going to start off with really just contextual. This is the Earth Science Division, and AgMIP support falls in there, right, in research and analysis. Flight, which is about 2/3 of our budget, is all those satellites. I'm going to talk about that a bit, but a lot of what I'm going to talk about is where I am, and I'm on the end where there's people, and I like that. We didn't do that on purpose, but on applications, on applied research, and that's really where the rubber meets the road. So you're going to hear a little bit about what my job is at NASA, but also about my career in applying Earth observations to Earth decision making. And I did that in the military, I did that at USDA, and I'm now doing that at NASA. So you're going to hear a little bit of this thread. So hopefully this works. I'm really hopeful. First of all, there we go. And so I put up all these satellites, and this is a standard NASA presentation about the Earth Science Division satellites. This doesn't even include the Copernicus program from ESA, all the commercial satellites. So in one sense, this is exciting. The other sense, especially for those of you who have to use this data or try to use this data, it is very intimidating. It's like, what are we going to do with all this data? We don't even know how we're going to download it and store it. That's a major challenge. How do you then integrate it? And then the introductory speaker from USDA talked about how are we going to get this information, all this data, and the information then in front of users, producers, agriculture industry to make it work. So I gave you that eye chart, but it does have a purpose. One of it is it's tough to find a satellite out there, both now and in formulation, that doesn't have an impact on agriculture and water. Really tough. And then you throw in climate change, even tougher. And so we have a lot of data being produced that helps us. But ultimately, all this is, and I say that very carefully, so with a grain of salt, all it is an observation. It's a sampling, often an imperfect sampling of the Earth. And where I've seen it best used is as a constraint. And that's why I love AgMIP. I love models, because the only way we're going to make and turn all those satellites into valuable information is through models. And very few I have a hard time thinking about those direct observations that have an impact, and that's outside, say, disaster management or disaster response. So with that, NASA is, and this, I think this is important for this community, really promoting an open science formula now versus the old data system, old DAC system that we have, where we have an open system where we can promote what probably AgMIP has been doing for a long, long time: co-development, collaboration on development, collaboration and sharing of algorithms, documentation. And so this is a bit of a announcement in a way, and you may have heard it from others in a much better way, but starting next year, you're going to start seeing more and more of the announcement of this. And this is really an idea and formulation. I really encourage this community in particular to step forward and say, hey, we know how to do this. We know how to collaborate and to co-develop on modeling and develop higher level products, and really step forward and say, yeah, we can help you help all of the community do this type of work. So I'm anxious for that, and you're going to see an application in my program too, where we're really developing this concept out already. Applied Sciences program, we focus on the end user. So most of what we do, and I would say there's two types of applications, one top down and the other bottom up. And top down applications in climate have been most of what we've been doing. We've been trying to develop out policies, trying to understand, get the right data, the right formulations. We're starting now to see the bottom up pull. And that's what I love to see, because I see those as really the sustainable tools that will develop out. That's starting to evolve now. But I would say one thing we have to watch when we do this, and let's see if my animation works. You know, these are bottom up. So how does a user make decisions? Not how a scientist makes decisions, not how USDA or NASA would make decisions. How does the farmer in South Dakota, where I'm from, make decisions? When's he going to tile? What crop is he going to use? What type of program is he going to select? What type of seed is he going to select? Solution oriented. We're defining solutions. We don't define data. What is the decision? Get really down to brass tacks. And finally, it's not the best science. It's the most appropriate science, built on a solid foundational program, which I'm proud to say NASA has. We have this solid RNA program. That's the foundation of what we do. It likely won't end up as the ultimate solutions out there. There's going to be aspects of it, and that's what we call appropriate science that targets a specific decision. And sometimes there's constraints on that science. Sometimes it's a latency issue. We can't wait to process all this data. We have to know this in 24 hours, not 2 months. How do we, what type of data can we provide in 24 hours? Let's go to my program, Water Resources and Agriculture. Actually, it's 2 programs. And part of Water Resources is a standard portfolio like NEFA has, like many of the NASA programs have. And I'm going to talk about a few of those projects. And we just awarded 30 of those projects. Over 15 of those water resources projects have an agriculture component to them. Not surprising. We also, though, realize that we can't manage and develop user-centric, solution-oriented solutions from Washington, D.C. That's where I work. And so we're trying out some new concepts. One of those are, we have obviously in the U.S. West, especially, and you could argue it all over the U.S., we have a serious water challenge, understated. And so we developed a program called the Western Water Applications Office, and we put it out at JPL in California to really start working with all the basins, with all the stakeholders out in the West that are trying to meet this challenge, and to develop a more persistent relationship. Number one complaint on NASA by end users, by stakeholders, is we're there for 3 years and then we go away. We fund a project for 3-4 years, then we're moving on. We develop a satellite that lasts 5, 6, maybe 10 years, and then we're on to the next thing. we want to develop some more persistent relationships. The Food and Agriculture program is all about that. And so we outsourced the program basically, and we competed it. University of Maryland won that award 5 years ago. They are actually going through a process of renewing the global component of that at University of Maryland. So NASA Harvest will continue on. Right now, they're out at Living Planet and basically have been consumed by requests about the Ukraine crisis. And so they've been doing a great job, but we then are competing, and proposals are due June 17th on a domestic consortium. So this one would really dive in to US domestic agriculture. So if you haven't seen that, please take a look. So our ROSES process, like I said, over 50% had agriculture applications. A couple of them, I'm going to talk about our irrigation scheduling component activity. I heard a lot about AgMIP and a lot about, hey, we need to do multi-model assimilations. Well, we agree. OpenET is, what really made it a success was that it was a multi-model assimilation that really produced and pushed it over the edge of really being successful. And we're still doing the model comparisons. We still have a lot of research that's being done, but that part of it really made it work. And then of course, things like working with the US Drought Monitor. They're defining the application and telling us what data that they need. Our Western Water Applications Office went to all the basins, working directly at the basin level. And then we fund projects within that basin directly to the stakeholders. It may be the Texas Water Authority, it may be a contractor. So things that they're working right now in the basin, to start working with them, start getting them to use Earth observations. And obviously they have a lot of work to do. And they also help transition our irrigation management tool, OpenET. Then of course, NASA Harvest, I mentioned that before. One of the things just to note why we're focused on the end user. One of the big things that happened in the past few years with COVID was, hey, we actually had pretty good production around the world, but users were going, why am I seeing rising prices? Why am I seeing all these supply chain issues? And so we realized right away that our production and yield information, if it's not tied to the transportation of that data, that product, that food to an end user, it means nothing. It means very little. And when those food supply chains are disrupted, you can't rely on the standard trade information and the trade system. And so we're developing out a tool now, and actually got put to use in the Ukraine crisis, of where are the impacts? Okay, crop is not going to be exported out of Ukraine, so what? Who's going to be impacted? Where are their options? So tying those into those decision-making activities is so critical. And then, of course, I mentioned this, and you'll notice on the right there, our domestic consortium. But we also have a division director who directed me, and they grabbed Alex Ruane too, and said, you shall go to the Commodity Classic and talk directly to ag producers, ag associations. And Alex, you in that picture, or were you gone?
Leave. I had to leave. I'm not there.
You had to leave. Yeah, you missed it. But yeah, Alex was there talking to associations, talking to ag producers, really putting NASA in both an interesting but kind of an uncomfortable spot. We got a lot of pointed questions like, why are you here? What's NASA doing here? And so one anecdote was one of our scientists was talking to an implement dealer, and they were pretty gruff. They kind of said, what are you doing here? Yeah, why are you here? And right behind him, right in front of the implement dealer, they were showing soil moisture data from the US Drought Monitor. And it was right out of our gray satellite with the big NASA logo on it. And he turned around and he said, that's why. And then they had a great conversation. And but it's the type of thing that our division director is really pushing us to do, is to tie into these big commodity groups. And obviously with Partnership for Climate Smart Ag at USDA, that was the big topic at the Commodity Classic in March. So really interesting discussions. And I know Alex has been following up. We had a meeting with some interesting people out in Iowa, really educational after that. Just some examples of the projects. I know I'm running at time and I want to make sure you guys stay on time for all the other speakers. But if you have any questions on some of these projects, including some of the work we're doing on greenhouse gas and in collaboration with USDA and some of our partnerships with the USDA, let me know. And I'm going to move on. We talked about NASA Harvest, and so I'm going to try to go through these slides a little bit quickly now. One of the things NASA Harvest focused on early on, as they knew right away, as many of your speakers did, is that if we don't bring the economic component into this, you might as well not talk about climate change. So we have to bring in that yield component, or I'm sorry, that yield, that profitability component, and right up front. And so they've been working with at Stanford. I know there's been other work, and I saw some of it in your presentations on assessing the impact of tillage practices and yield, and where you can actually be profitable and do no-till. So it's one of those things, we think it's obvious, but when you see the uptake, it isn't, and we need to make this information more and more available to those producers. And of course, working directly with AgMIP, trying to integrate this data. So just wanted you to know that we're really the modeling component of this, and getting those models robust and in front of these producers, I think is a challenge, but also going to be a huge game changer for our community. OpenET, I just want to mention this real quickly. I encourage you to go to the site. Once again, just like AgMIP, a consortium of end users and co-develop. You'll notice in here too that we actually have producers, Almond Board, Navajo Nation, Texas Water Development Board, co-developers in this. And I really encourage that as we move forward. And I saw the Iowa State Extension Service. You know, if we wanted to do one thing right now and fund one thing, we ought to just fund all the extension services, double their budget, because I just think that is a tremendous way of really applying what we're doing. And when you talk to end users, like at the Commodity Classic, they love their extension service. They love their local land grant universities, and we ought to be using that as a way to really move and make climate smart agriculture work. Sorry about that. I just worked it right in. And one of the things you'll notice here too, I just put up this slide, and this is actually an extension service application, tying the data into existing tools. We found that, and we're doing that with OpenET. So OpenET isn't necessarily the tool. It is, we're working with end users, irrigation companies, to where our tool is integrated so that the end users is using their irrigation management software. And but our data is integrated into that. So I think that was another way of really making this succeed and work. And finally, carbon monitoring system. I'll just throw this out. A lot of you know about it. A lot of you have been funded by the carbon monitoring system. It's a 10-year program that was ahead of its time. Basically an applications program in the research group, but it was an applications program without an application. And now we're getting the applications. We've done all this great work on prototyping, all this great work on demonstrating. Really, you know, we're ahead of the game, and now we're going to start seeing the pull. And I'm really excited to see, you know, phase 3, 4, 5 of carbon monitoring system, because I think we're going to start seeing those transitions, those uptake of a lot of the technologies that they developed. And one of those obviously is really pushing hard on LiDAR. We have some work to do at NASA and keeping a space LiDAR on the books, and we need to fight for that. It's a tremendously important part of our ability to assess biomass, both forestry, and I don't think we even touched a lot of even the basic research on doing that in other vegetations like cropland. So with that, I'm going to skip through this, and I look forward to the panel discussion. So thank you so much.
Well, Brad, thank you so much for the wonderful presentation, the great overview of all these exciting programs. I know many of our colleagues that are more on the land grant and the USDA side of the world know of the NASA programs, but this was a great way to get a better appreciation. And I have to confess, I could hear in the back of my mind extension agents across the country shouting and cheering your comments there. I'm sure they really appreciate that. And I know this is an emerging topic in the extension community as to how they can be more supportive and on the ground in that interesting position between working directly with farmers on an ongoing day-to-day basis and understanding their practical problems and trying to help us formulate the kinds of questions that collectively we need to all be helping them address. So thank you so much for that. And I'm going to go ahead and segue now into our panel. Our next speaker is Dr. Fred Pierson, who's with the Northwest Watershed Research Center and is with USDA's Agricultural Research Service, and also we'll be looking at this bridging between the NASA satellite tools and resources and work that's being done in collaboration. And Fred, I'm going to release the screen and hand it over to you.
Okay, let's see if I can get up the right screen. Everybody can see the screen okay?
Looks great. Thank you. Go ahead.
So yes, thank you very much, and good morning. I wanted to talk to you today some about a very fruitful and productive collaboration and partnership that we've had with NASA. It feeds right off of what Dr. Doorn was talking about there with sort of the bottom-up approach to trying to solve water resource problems, trying to give water managers what they need, but by sort of combining remote sensing and simulation modeling. So this has been a really good collaboration and very productive. So I just wanted to sort of walk through a little bit about that. But first, I just wanted to answer some of the questions that I often get. It's like, the Agricultural Research Service does snow modeling or snow work. And so just to build our credibility a bit is, yes, we do. We've done snow research in Idaho at the Reynolds Creek Experimental Watershed since 1960 or so, and been very instrumental in the development of technology for measurements of snow, all the way to the development and testing of the snow pillows and a lot of other instrumentation over the years, and done a lot of snow modeling work. We have quite the background in the snow sort of physics and dynamics. So what I wanted to talk about here was that when we talk water supply for the Western US, a large part of what we have to talk about is how much water is available and held in the mountain snowpacks, right? It's a little different than some other parts of the world, but out west, it's very much about what happens in the snowpack and the translation of that snowpack to stream flow. So the stream flow there is, critical for a whole diverse set of needs, of which agriculture is only one, but power generation or municipal water supplies, but also is managed through a series of reservoir storage units that really serve to sort of move the water into the dry seasons and or dry times, and also helps with flood protection. So water managers are always challenged with this balance between saving enough water for all the use, but not saving so much that you can't store the flood. So that's always a huge management problem. So in the past few decades, there's been these, huge episodic climate-driven droughts throughout the Western U.S. that obviously you hear about, Lake Mead and so on these days, and the dry problems that we're having for the lack of water. And so, the thing that we're working on here is trying to improve the forecast from the snow so that we can do manage a more timely, better allocations of that water to the different needs. So the traditional way of forecasting how much water is in a snowpack is simply to measure at a few points within a basin, right? And then take that and just do a simple correlation with, if I have so much water at a certain point in time, then I'm likely going to get a certain amount of output of stream flow from that basin. It's really just based on a historical record of inputs and outputs. And so it requires a long time periods, which we have had with measuring snow, say in the Sierra Nevadas and places for, over hundreds of years, 100 years. And so, but what these things don't account for is climate change. As the system changes, obviously the period of record is not applicable any longer, but also for forest disturbances and climate extremes like the droughts and the things that we're see the big swings in wet years and dry years that are not represented in the past. It doesn't fit that very well. And then the dominant processes for different snow components, whether it be rain on snow and that sort of thing. So there's a lot of shortcomings for the sort of traditional approach. The modern sort of where we are now, where snow science is significantly evolved over the last couple of decades, is that one of my scientists, snow scientists, likes to determine is the spatial revolution in hydrology is this idea that we're talking about is there's tremendous amounts of sort of remote sensing snapshot measurement information that's now available, but how do we make that really usable and tangible down to a water resource manager? So, but the tremendous opportunity that exists is that the current and past sort of predictions are based on just a handful of points, 10 points, maybe 20 points of measurement within a very large basin. Whereas we have an opportunity with remote sensing and things to start having millions of points of information within a basin. So how do we make use of that, but yet still boil all of that information to a user, to the end user? And so the other thing that's moved along that we all know basically though is that the tools are finally catching up with all of this data, right? So the data management or analysis tools exist, but also the computational sort of capacity. We've honestly had models that we could run, say for some hydrology models for some quite a period of time, but to think of running those process models over the domain of the entire Sierra Nevada mountains at one point, continuously, and then getting hourly outputs and all that, be able to manage that and run that computationally is a huge challenge. But in today's world, we can do that. So, so in our case here, really is how do we take all that information and these possibilities and boil that down into what is the stream flow going to be given how much snow we have? So the collaboration here between NASA and ARS really was that in about 2012 or so, NASA JPL began to develop what they called the Airborne Snow Observatory, which is an aircraft running LiDAR and spectrometry and across a watershed. And so what that does for us is provides us a very accurate sort of what the snow surface looks like. So from that we can tell before and after snow is that what is the snow depth. So we get very accurate many points of information in a basin for the snow depth. But what we want to know is how much water is in that snow, not just the depth of the snow. And so that's what's called the snow water equivalent, or how much water is held. And that's where the modeling comes in. So you really have to have a density and the state of the pack, how much is melting when, and that sort of thing. So the modeling, the detailed sort of physical modeling combined with that information of what does the snapshot look like on a given day of the snow depth, really allows us to start to give daily outputs of snow water storage estimates over every square meter of a large watershed. So again, going back from having knowledge about just a few points, we now can produce information for many points, or millions of points within the watershed, essentially. So just as a sort of example, rather than talking so much about how we did that, I wanted to talk about how sort of where we've tested it and the impact that we're seeing from this, and where we are with the applications of tools and working with the managers. So the focus has been for our sort of R&D or development testing and first implementation has been in the Sierra Nevadas, which is the Central Valley. Agriculture relies heavily on sort of that boom or bust of snowmelt runoff. And it is a huge agricultural production area. Some of the highest ag producing counties in the country feed from this water that comes out of these basins. It also happened to coincide that at the time we were working on this collaborative effort was that the California was in one of the most significant droughts it had ever seen, basically. And then by Jove, sort of whiplash, you come back around and have one of the wettest, some of the wettest time periods with very high snowfall. So you have this swinging sort of climate and climate inputs and outputs to really look and see what we're doing or how well we're doing. So in 2013, ASO and iSnowval, the modeling that we developed is called iSnowval, but the physical-based modeling, we're beginning to provide basin snow water storage for the very first basin in California. But by 2019, we were up to modeling 5 large basins in the Southern Sierras on a day-to-day basis, and for each throughout the entire season. So really in those few years, it went from just being able to how do we do it to starting to really demonstrate that we could do it over those large areas. So where do we sort of sit today is that we now have basically what we call a modeling framework. It's more than a snowbound model. It's a lot of infrastructure within the modeling, essentially, well beyond my expertise, to be honest. But we can now operate that over very large basins, and it's really for the whole state of California, say, with seamlessly incorporating the satellite and airborne data sets for model assimilation. So we now can just take in whatever information does exist into the model and assimilate between those two very important sort of pieces to the puzzle. We're also assimilating other technologies such as the HRR modeling, which is a gridded atmospheric forecast from NOAA, as the snow model inputs. And so that is also one way to start assimilating other information. And then what we can do now is basically sort of manage all of this. It's the management software that allows you to run this in the background virtually on any platform using the automated workflows. So it's a lot of science, but there's also just a lot of technology or sort of a computer science here as well. So just sort of an example, I want to focus on how important these kinds of marrying these kinds of technologies and then abilities really can be. So this is again an example coming from the California work where it's about management of reservoirs, as I said, and though the water managers are essentially legally mandated to consult stream flow forecasts from 2 different sources. So the state law basically says they have to consider these 2 sources of information, and they're built on, the first one is the Bulletin 120 from the California Department of Water Resources, and that's essentially, as I described earlier, it's a very sort of so many points of measurement of what's incoming gives a statistical relationship to the stream flow that's leaving the basin. So, but that's the traditional way things are forecasted, and they put out a formal forecast that must be sort of managed against. And then as the California and Nevada River Forecast Center puts out a more sophisticated modeling approach, but they look at sort of, again, the past history and look at it from an ensemble stream flow prediction perspective, and some fairly basic physical modeling underneath that. So those two forecasts that are utilized to manage water in California. This is just an example of the kinds of events or timings that where something like the ASO ice snowball kind of tool can come into play. So in the San Joaquin River itself, that comes out of the mountains, it comes down into a reservoir called the Millerton Reservoir, and it feeds into two very large canals and feeds out to 34 water districts and municipalities and 15,000 farms. So this water, you know, it hits and touches many downstream, right? But again, so the management of that water is extremely important to all kinds of sectors downstream. So it also, in this particular case, is instrumental to such things as habitat restoration for the Chinook salmon fishery in the San Joaquin River itself, coming from the delta or from the San Francisco Bay. So just one sort of event or one time when this kind of technology is extremely useful. So the Bureau of Reclamation manages this particular water or reservoir. And so when you look at the two mandated predictions here, that in this case they were very far off. So that one's as much as 420,000 acre feet. So that's how water managers talk about the waters in 1,000 acre feet. And there were, so the forecasts were differing by 420,000 acre feet when the overall storage within the whole system was only 385,000 acre feet. So they had this error between forecasts because of a pretty anomalous year, basically, of snowfall, that they were having these very different forecasts. They didn't know what to do. So utilizing a tool like what we're talking about, where you can fly over, take a snapshot, figure out literally where the snow is, how much is there, and what state it is, and how much water still resides up there, is that, so in this case, it shows May 15th, they were off by 1.5 million acre feet, right? So that's how much water was still up there. And they're looking at, you know, almost a third of that being a difference in the predictions for those forecasts. So given when they applied and utilized the ASO ice snowball products, you know, it really came down to that in the end of that year, they had ended up knowing about that water and managing that water to where they only had a 1.6% error from, you know, what it is they predicted would come out and what they actually got out. So a tremendous improvement for their ability to know what was coming and how to manage that water. Where are we with as far as the sort of transfer of the technology? You know, the science and development of these products is forever continuing. It always does. But the spinoff for where we reside today, essentially, is that the operational modeling airborne LiDAR is occurring now across the Western US and has been privatized in what's something called the ASO Inc. And then a spinoff from that, the modeling is the M3 Works is the modeling component. So still keeping the flights and the modeling combined, but now it's privatized and actually doing it for the water managers in a number of basins in California and in Colorado. So there's a operational ice snowball pilot program in 6 Sierra Nevada basins with the California Department of Water Resources. So the state agency is literally running this system themselves. They still need the LiDAR and still acquiring the LiDAR, but they're able to take the LiDAR and run the model and run the system itself for their own uses. That way they can start to answer their own questions, play their own what if games. You know, it's putting the tools into the hands of the actual users. Some other cases is that we are working in the Colorado Basin River Forecast Center is beginning to take a look at the model as well, to look at runoff forecasting as well. And so some beginnings, at least for some international collaborations as well for interest in the modeling system. Again, this has been extremely fruitful, albeit it's never done. There's always better things out there, but it's a great example of a modeling system built sort of from research, but now being able to be sort of constrained and augmented with snapshot remote sensing information, and then putting it truly in the hands of the users, right? And so, but there's plenty of more opportunity coming down the line for additional sensors, whether they be satellite, whether they be airborne. There's other things to measure other properties of the snow besides just the depths. So we are particularly looking forward to being able to try to figure out how to assimilate other information as it becomes available. And we work through that through the NASA SNOWX program, have been involved in that for a long time. We'll continue with that, but also looking forward to some of the future satellites, NISAR and others, that when we can start to do more of a confining on the actual suite itself and things, perhaps, rather than just so I think that's all I have to share for today.
Well, Fred, that was a lot to share, and thank you so much. It's really exciting to hear about this collaborative work across multiple agencies, certainly between NASA and USDA, but across ARS and NRCS and the state entities as well. Hopefully we'll have time for questions and discussions, and I know one of the things that I'd like to explore further is marrying up future weather or climate forecasts and running those kinds of what-if scenarios because of the obvious implications of the availability of water for irrigation and for our agriculture and food systems, both nationally and globally. So a lot to build on from there. But for the moment though, I'd like to move forward. And real quick, I'm going to share a screen for a moment. And our next speaker is Dr. Stephen Mirsky, who's with Sustainable Agricultural Systems Laboratory, again, USDA-ARS. And he's going to talk about operationalizing precision, sustainable agriculture through on-farm research and the long-term agroecosystem network, the LTARS. Stephen, I'm going to release my screen and you can take over.
Excellent, thank you. Can you see my screen?
Yes.
Looks great, thanks.
All right, wonderful, thank you. Well, I appreciate the opportunity to be part of the event today. I'm really glad I got to sit in today and listen to all the speakers. I haven't been here for the whole week, so I can already tell from some of the opening slides I have that a lot of this has probably been covered. So I'll just sort of breeze through, but really enjoyed the previous speakers, and they made my work and the concepts I'm laying out, what we're doing, pretty easy. So I'll try to speed through some of this front end material. So as we know, we've got to feed the world. We're going to scale this food production systems up in the next couple of decades. And it's not just, increasing food production. We have all these destabilizing factors. Climate change has been sort of, talked about a lot, I'm sure, throughout this event. But, there's a lot of other destabilizing factors that also interact with climate change, like competing water demands. We've got, many of our pests are resistant to most of the chemical options we have, particularly in the case of weeds, and the continuous declining of our soil and water quality. To meet this challenge, we really need to develop more precise and sustainable agricultural systems, so sort of climate smart farming being that. And so what I'm going to talk a lot about today is our efforts to develop climate smart farming practices and how to operationalize, really not just that do the practices, do the thing, but how do we get farmers to adopt these practices and make them, very palatable and accessible? And really that for us is being done through merging of precision and sustainable agriculture, precision being that site-specific management, the highly ability to be adaptive. And then in the case of sustainable agriculture, we're talking about regenerative and resilient systems here. These are a lot of practices that have been, well documented and studied and used by many farmers. And these are sort of the premier strategies for developing more regenerative, resilient systems. But merging precision and sustainable agriculture is challenging. These are, really knowledge intensive practices. And so by combining them, we really need a lot of data and information about how climate and soil and management interact to drive function. Here you can look on this field on the left. We've already seen a lot of, from Bruno's presentation, the degree of spatial variability in a field. This is just showing that, the drainage in a field is affecting performance of the cereals at a high degree on the left. And you can see here on this image of the corn grain yield that there's a lot of factors that contribute to that deficiency in meeting that yield goal. And so trying to break that apart and understanding that and manage that complexity is what we need to be able to merge precision and sustainable agriculture. LTAR, the Long-Term Agricultural Research Network, is a key part of this storyline because they're developing the long-term data sets. A lot of this event has been about models. Well, these longitudinal data sets are critical for understanding how management drives changes in soil over time. And the LTAR is really sort of the premier resource for that. And so they're developing a lot of coordinated science, community of practice, as well as a common experiment. This common experiment is sort of contrasting business as usual practices, sort of what is the prevailing practice in a given region and system, versus aspirational systems, what represents sort of the most innovative, early adopted practices or practices that have come with a lot of enhanced agroecosystem services. And the LTAR network was strategically distributed across different range and cropland systems to sort of capture the scope of agricultural systems in the US. However, in-depth trials on research stations alone, can't fully capture the spatial complexity of climates and soils, and particularly the complexity of farm management. Therefore, we need to sort of reimagine the landscape as a living laboratory, and low-cost sensors are really sort of the key way to get at that, to be able to quantify how climate and soil management intersect and vary across the landscape. And so we develop a lot of these low-cost sensor systems in our long-term cropping systems experiments, on our research stations, and then are deploying them in our on-farm networks. And so it's really that linking up of the longitudinal data that the LTAR gives us with what on-farm research can provide for capturing the spatial complexity of the soils as well as the management. But I want to sort of really chime in on it's not just bringing together longitudinal data and spatial data to inform, build the models and the insights, but it's really how do we go about creating transdisciplinary teams and building those translational pipelines are what's really matters for how we operationalize this. How do we take something from the realm of science that, are we studying what is going on in the landscape, how well does something perform, versus to the realm of practice that farmers are using these practices. And so transdisciplinary science brings together researchers of different disciplinary focus. It brings together farmers as collaborators in this enterprise, and brings together the private sector, all to sort of create this pipeline of both integrating the multidisciplinary science and then building these translational pipelines so that it's not just a proof of concept, but that we operationalize both the technologies that are used and the practice. And so I'm going to show two good examples, I think, that are doing this. These are two teams that I helped to co-lead. It's the Precision Sustainable Ag Network on the left, which is a national on-farm research network. The circles with different colors in them represent activities on station, as well as the smaller circles are farmer partners. And this is not a fully up-to-date map. We have a lot more farms present in the Midwest and South Central that is exhibited here, but it's, we're in sort of hundreds of farms per year monitoring using low-cost sensing technology. And all of the practices we're studying are, climate smart focused practices. I mean, the main commonality right now is cover crops. So we're sort of heavily focused around the cover crops, and key members of the cover crop councils and leaders of that are key members and leaders of the Precision Sustainable Ag Network. But we also are looking at reduced tillage systems and precision nutrient management. And on the right is a heavy focus on integrated weed management. This is the GROW team, another national network focused on developing, more integrated management strategies, using precision as well as cultural strategies to address the issues that, we're running out of chemical control options in our weed systems. And from a climate smart perspective, weeds are sort of a big driver, because we're seeing a lot of farmers now turn more to tillage to manage their weeds because of resistance. And, that's going to be a real challenge for us when we're trying to develop more climate smart practices. And I just want to emphasize that, a lot of this really comes from public-private partnerships. So, we're at ARS, we're NRCS, we're over 28 university partners. We have deep partnerships in agribusiness equipment and the chemical companies, strong collaboration partnership with the commodity boards, a number of technology companies, as well as the public on-farm network we manage, as well as private on-farm networks that we partner with. And I think this is sort of give the gist of this translational research comes from these strong transdisciplinary teams. So, but it's all about making the data actionable, right? It's not just collecting data. How do we act on that? How do we use that data to inform decision-making in either near, to real time, or for that long-term planning? So, we build highly structured, queryable databases that connects vastly different metrics, both on our on-farm networks as well as our research stations. We build APIs when they don't exist to real-time weather data, or to link up Sergo information, so that we can have that all integrated into our databases or to inform our decision tools. But it's not just about the data, it's really about the community of practice that I think is really important here. We're very siloed away in the public sector, and so it makes it hard to sort of link up how climate and soil and management intersect, because we're all sort of working in our own system. So how do we break down those data silos and coordinate our science so that we can do this in a way that builds data standards, quality control, and ensures the success of the enterprise? So we focus a lot on the human aspect of this, really. I mean, it's, getting humans to be consistent on the use of a protocol, on the standard use of a technology, to how we, the timeline in which they share that data, that these are rich challenges in large team science. So we built intranet portals so they have real-time access to the data, real-time access to the protocols. If there's any changes, we have lots of links to our, transparency with our source code, to our GitHub repositories, how our databases are structured. We've got how-to videos that we make on YouTube that makes it available to the scientists so they can, in real time, if they have problems. We have hotlines, so any 40 hours a week, they can call in if they're having a problem with the deployment of a practice. They have a hotline they can call to get their solution solved, and keep moving. We automate data collection with web-based applications. We're building technology dashboards so that our data shepherds, as well as our technicians, can in real time see, is the data flowing? Is there a problem with the sensor? And if there is a problem, we can act on that quickly, because we can see in real time if there's a problem across the network. And then we're also build task trackers. Did you collect the data? Did you not? Where are you at? I mean, we have endless real-time assessments of where any one state in a partnership is, so they can check, are they doing the thing? Are they getting their data into the technology dashboard and making sure that it's in the database? And then ultimately, all of this builds models. So we've heard all about models, and we have a number of process-based modelers on our team, and we have a lot of empiricists, and we're building expert-based tools, process-based driven tools, and all of these then become web-based apps that are for decision making, both in that real time as well as for that long-term planning. Here I'm highlighting some of the tools from the cover crop councils. This is the Northeast Cover Crop Species Selector tool. I'm really excited about the partnership between ARS and NRCS to help usher in and co-lead national efforts about building these web-based decision tools. So working with the councils and Precision Sustainable Ag, we're building species selector tools, seeding rate calculators, economic calculators, water and nitrogen calculators, all to sort of build these ecosystem of tools that help inform practice, as well as a number of other conservation practices that we're working with the plant material centers that are all fit under sort of these climate smart strategies. And these will be, national resources with their own site specific recommendations to serve, farmers and ag professionals. So, when we aggregate and break down our data silos across these national networks, we put that into our databases. Those databases are, fitting into our models and our decision tools. And then we're doing this on-farm research. Well, that on-farm research is being done by farmers who are also using our tools. And so we can be continuing to monitor and map what's going on those farms. That data feeds back into our databases, and it creates that positive feedback loop of continually improving the precision of our recommendation systems to growers. So I want to sort of just give a small use case example of what these large scale teams can do and how transformative it is. I really loved all I saw around what's being done with satellites, and our team has certainly a rich body of work that we're doing with satellite imagery. But there are a number of limitations to satellites. From satellites and even drones, you can't really get species specific information about what's going on across that farm field. You can't map different species or species and mixtures. This is particularly important if you want to differentiate weed species from crops, differentiate cover crops or mixtures of cover crops. So the first step in this is that you have to build high resolution open access image repositories, right? That's the resource that we're focused on. So it's a public good that anywhere in the country, from private sector, the public sector, they can use this resource and innovate on this resource. But it's incredibly costly to do this, right? It's very difficult for the private sector to take this on. You need tens of thousands of images of every one plant, and you need to do this for the diversity of species that are out there, and you have to do it over a wide range of growth stages of that plant. You can see just from the schematic the number of aspects of a single plant that we're capturing. So networks like ours can go across the country, build these high resolution image repositories, and then they become a public good. And I just want to show you an application of these image repositories. We can then take these image repositories and train low-cost cameras that are then mounted onto our, for example, in this case, a spray boom. And this is really powerful because, farmers are going to be driving across every square inch of their field, no matter what, multiple times in a season. We need to have cameras on the front of those tractors, those booms, or however they're mounted, depending on the instrument, to be able to map what's going on out there in real time. These low-cost camera systems here are using stereo capability, so they can create depth maps, and an RGB camera in the center that can do species identification. So in real time, we're mapping the species and the biomass that's out there. And that's really potent because then we can also start to get at this quality and quantity. Knowing the species, knowing the biomass levels, we can then get, for example, in the case of a cover crop, how much nitrogen is in that cover crop. We can have high resolution pixels of 20 foot by 20 foot increments in a field that we're now providing precision nitrogen management. Furthermore, our teams are making these decision support tools using process-based models to inform how cover crops decompose and release nitrogen into the soil. Well, we can then feed these pixelated maps back into our tool and provide those detailed recommendations to the growers to help improve their nitrogen management. So thank you for the opportunity to share some of the work that we're doing.
Well, Stephen, thank you so much for sharing about the LTARs and the precision ag and the sustainable ag systems. It's great to make that complete bridge to the from satellite down to field scale, and I'm still trying to get my head around the volume of the database or the number of photos and entries you're going to have to sustain over time, and look forward to talking further with you about how we can take good advantage of all of the resources you've been developing there. Our next speaker is Dr. Jonas Jagenmeyer with the Center for Climate Systems Research here at Columbia University. And he's going to talk about next generation modeling and AI. And Jonas, you may be elaborating on the title and the topic as well, but why don't I hand it over to you?
Great. Let me share my screen. Well, hello, everybody. So I was asked to share my thoughts on the next generation modeling and machine learning. And, obviously this is such a rich field. Even just the presentations we saw throughout the last 3 days is way too much to attempt a comprehensive overview. So what I'm going to do is I just share a few projects where I'm actively contributing to, and then share some thoughts where the field goes, and take it from there. So I'm Jonas Jaegermeyr. I'm with Columbia University and NASA GIST in New York City, and I co-lead the global gridded crop modeling within AgMIP, GGCMI, and also the agricultural sector in ECMIP, the cross-sectoral model into comparison that tries to harmonize not just the agricultural work itself, but then across impact sectors such as energy, water, human health, and so forth. So as you can tell from my background, I'm coming from the global perspective. So my thoughts and projects and thoughts I'm going to share are definitely coming from the global perspective, but much of the lessons learned do apply across scales. And I think that's interesting to connect to the more high resolution, fine scale work that we've seen before to the highest global, the highest level at global level. I want to start off with highlighting our recent multi-model ensemble work that we did in AgMIP and ECMIP with the global crop models. Because it represents the core idea of AgMIP and ECMIP in the vein of CMIP, approaching the question by default with a multi-model ensemble and a harmonized protocol. And that is now the default standard in these kind of long-term future estimates of climate change impact. You want to get to more robust estimates with the multi-model ensemble, and using a single model for 50 years plus outlook is just not appropriate anymore. So here I'm just going to share real quick what we call GGCMI CMIP6 multi-model ensemble, using CMIP6 GCMs that are bias adjusted and downscaled centrally by ECMIP for all these input sectors for different SSP RCP combinations. And as of today, we're bringing together 12 gridded process-based state-of-the-art crop models that all run at a half-degree grid globally, which make about 240 simulations per crop. And these process-based global models are very computationally expensive, so they all run at a supercomputer somewhere worldwide, and we're bringing together the community, trying to harmonize their inputs and assumptions and the protocol in general. For this work, we created a new observational crop calendar. We're now doing yield bias corrections by default, so we're not averaging yield estimates from various models, because different yield levels, baseline yield levels, will lead to a bias. So we're doing a bias correction to compare the models, and obviously we have mechanistic CO2 responses. Importantly, this work is isolating the climate signal, so everything management is kept constant for now for these long-term outlooks. The slide shows neat animations done by the NASA News team, showing this new ensemble of record, the new simulations that will be run for a while, averaged across the different domains, showing distinct differences between crops and regions. And we need to understand better where these come from and how we can develop adaptation pathways across different regions that are viable to implement. One of the main findings from the new work is that the new simulations based on CMIP6 are substantially more pronounced. And by pronounced, I mean more pessimistic for most crops, but some of the crops show higher potential gains, especially in higher latitudes. With the gray stack here represents the previous CMIP5 based simulations from Cynthia Rosenzweig's landmark paper in 2014, showing a global response for maize end of century for RCP 8.5 of +1%. And now the new CMIP6 based simulations drop down to -24% end of century. So that's a stark 25% difference within what, 7 years of advancing models and inputs and protocols. That's substantial, that's huge. And we need to do more to reduce the uncertainty that is still associated with it. The two vertical lines, the dashed line and the solid line, indicate the range of the climate models, and the solid line indicates the range of the crop models. For RCP 2.6, these ranges are largely similar, but as soon as we move to a higher emission scenario, the range of crop models is substantially larger, inflating the uncertainty, which is obviously a problem that needs to be addressed. Another way to look at this is the amount of induced variance. So for this stack, this is the CMIP5 based ensemble. Virtually all of the variance is induced by the crop model ensemble, 97%, and only 3% out of the climate models. Now in the new ensemble, the response is more balanced in terms of absolute variance, but also in relative terms, which is good. And it is consistent about crops across crops. So now about a third of the uncertainty is associated with the climate models and 2/3 with the crop models or impact models, if we can generalize. And these numbers are consistent in different impact sectors, which means the impact models still dominate the source of uncertainty. And that's an aspect that needs to be addressed in the future. There needs to be targeted model development. There needs to be concerted efforts to improve the models, the input data, the protocols, and everything associated. One way to do this, and we're actively engaged in model development and on several fronts, and not just us at the global community, crop modeling worldwide, obviously. One of the prominent blind spots is excess moisture or waterlogging. Here on the left-hand panel, US Corn Belt yields provided by USDA-ARS shows that leveling off, the decline with very high levels of precipitation. And the crop model response, this is the CMIP6 based crop model ensemble, for rain-fed yields shows no response, no leveling off at high precipitation anomalies. The irrigated side does to some extent, but that's a problem we're currently addressing, and it leads to the fact our prominent time series with the prominent year 1993 with the floods, that we just can't explain the yield declines in that year associated with flooding and excess moisture. Several teams are working on that. APSIM just has a new waterlogging setup. We're aware of the problem. We're writing papers on that. And one extra component is that it's not just or let me say first, the many of the current crop models do have the processes that respond to waterlogging and excess moisture, but it is the soil water conditions that do not lead to the conditions where they would actually come into place and affect the yields. So it is more of a drainage problem, a soil component problem than a process representation, which is obviously difficult to address. Another way to improve on the modeling response is to bring in a flooding map that can address the physical damage to crops in post-processing. So we're collaborating with colleagues who run flood models to bring in the data and then mask out certain areas that were exposed to flooding during the growing season. And then an indirect component is through planting dates. In 1993, much of the yield losses were actually not necessarily associated with physical damage through flooding or waterlogging or reduced temperature and radiation, but through delayed planting. And globally in our current modeling framework, we're assuming constant planting dates across years, which obviously is a big caveat that we're also addressing, and I'll talk to that in a minute. Another way where we're currently improving models is, for example, the response to atmospheric ozone concentrations. We're improving the DSAT and LPGML model to calibrating it for several crops to evaluate ozone concentrations in the future. And we also work on the representation of direct and diffuse radiation in order to evaluate yield responses due to atmospheric geoengineering. Speaking of planting dates, so for the global crop modeling work, we, as I said, usually assume constant crop calendars that we developed a new version of for the current work. But there is a wealth of data available that we can scrape and create an actual annual product, which I'm currently leading on this map for Europe, showing phenological databases from the Pan-European Phenology database, from the Joint Research Center and observations in France, about 18,000 sites across Europe for several crops, reaching back all the way to 1850, which is a tremendous archive of data. We're processing these, harmonizing them, interpolating them, creating annual crop calendars from 1950 through 2020 that can then improve crop modeling. But at the same time, it allows us to derive time trends, which is very exciting and is a data-driven product of an empirical product of climate change impacts on what's happening in the field. These kind of data are not only available for Europe. I just showed it as an example. We have annual data in a series of countries from Canada, US, Mexico, China, and most breadbasket countries. And stay tuned, this is going to come out and will be available. Now, another way to improve our modeling setup is the spatial resolution, obviously. Spatial resolution is linked to data availability. In AgMIP, we're currently carrying out a project, CHELSA, where we systematically evaluate going across scales at global level. So we're simulating half-degree grids, 5 arc minutes, 0.5 arc minutes, and half arc minute to find a sweet spot and to evaluate what the increasing spatial resolution can actually benefit based on the models and inputs we have. But also in-house, Alex, Ruane, and others lead projects setting up the DSAT model for very high resolution in Iowa to get a hold of processes that we usually can't address in our global models at half-degree grid. Now, a completely different story, but that's also important and constraining our crop models is the water availability in crop models. So we are trying to link crop models that have no representation of surface water with those ecosystem type models that run river routing to constrain the irrigation water availability in crop models and have a better understanding of future irrigation water constraints and requirements. This is actually addressed in a Aspen Global Change Institute workshop later this year, where we come together, and it's always a great incubator for pushing this type of community work. So hopefully at some point we can base these kind of things on better protocols. Now I want to talk a little bit about emulators, because that's a tool that is going to be more and more important. And in GGCMI, we set out a project where we simulate a multi-dimensional response surface perturbing different variables in a systematic way: carbon, temperature, precipitation, nitrogen, across these ranges, which obviously allows to draw these kind of response surfaces. But also, as Alex showed yesterday, we can put this kind of work into a dashboard or impact explorer that allows interactive user experiences, exploring changes across these domains. But it is, first of all, a training data set for building emulators. And we can, Jim Frank et al. Built a polynomial emulator. We can also create machine learning based emulators where we're training these on these multi-dimensional domains. Here, the work has been used to evaluate future yield variability, showing that the models indicate that yield variability is going to increase in much of the cultivated land. Then another in-house product that Alex is working on flips it around and using machine learning to learn about the process-based models. So the feature selection out of the machine learning algorithm actually tells us a lot about the sensitivities of the model. And just highlighting here too, the PD set and the LP-Jaegermeyr model shows that the DSET model is much more sensitive to the temperature variables, whereas LP-Jaegermeyr is mainly driven, or maybe mainly responsive to the precipitation domain. And then finally on machine learning, we're working on one aspect of introducing knowledge-guided machine learning. And knowledge-guided means that there's the feature selection, the machine learning algorithm is constrained by physical theory. So the output is supposedly plausible, which I think holds a lot of potential. And in that case, we're training a machine learning algorithm, or several in this case, on process-based model outputs, trying to improve the performance, the yield estimates then against observations. And here in the case of compound events where it's called GGCM, the process-based models show large biases, the machine learning trained algorithm obviously can create a much better fit to observations. Just want to, wrap this up and summarize the various thoughts I had. One big component is obviously higher fidelity. We want to improve process representations. We want to improve our input data and increase spatial resolution, which is obviously tied to computational requirements. But what I think is really important to learn about the strength and weaknesses of different approaches and combine them in a meaningful way. So we should, or I think we need to overcome this camp thinking that, my model is better than yours and we're doing process-based and you're doing empirical. Every model has its place and they should be applied where it makes sense. And I think particularly combining machine learning and process-based models has huge potential, and empirical models are really important for very short-term applications. Then obviously remote sensing data is critically important. We had a lot of talks focusing on remote sensing data, so that's why I didn't really go into that here. But remote sensing is important for all components of modeling, for the input sides, for calibrating the models, for evaluating the models, and then aggregating outputs. So it's a central component to improving models, especially moving up in scale. Management data is currently the bottleneck for improving the skill and the model evaluations. So what's really important is the consistency of data, and we talked about that a lot, and that links to cloud-based applications, to networks of networks. The ClassNet initiative is coming on, where all that kind of data is combined in an archive that is easily accessible and quality controlled across larger scales. Only then it is relevant for global scale applications. And I'm thinking of not only planting dates, but cultivar use, on-farm management, and all sorts of things that will really help improve the modeling and calibration of the modeling setups. The work I've shown so far mainly focuses on isolating climate change impacts. Obviously, there's a lot of work to be done to move beyond that and focus on adaptation and mitigation and co-benefits of the two, linking the work to SSP pathways and representative agricultural pathways. So that's going to become focus in the next rounds of simulations. And then we need to combine these realms of modeling. There's always the global modeling and the regional modeling, and I think we need to bring these closer together and learn and make them consistent. And then finally, the timescales are important. There's one thing to give end of century estimates, but it's more and more important to realize that, or we do realize, but it is more and more important to look at shorter timescales from next couple of years to really go to the end of season forecasting domain. So we are working on linking across these different scales. That's what I have. There's obviously so much more, and everybody has a subjective view of what's important in the next couple of years, but this is my take. So I'm more than happy to discuss, and thanks for the opportunity to speak.
Well, Jonas, thank you so much. And obviously, we've got grounds for a whole nother conference building on what you've laid out here for us. So many great opportunities. I'll need you to let go of the screen. There we go. And our next and final panelist for this session is Dr. Alex Ruane, and he's going to talk about building foundational models for climate-smart agriculture, kind of picking up from where Jonas was in terms of what new, better, different things we can be thinking about. And Alex, I'm going to release my screen and hand it to you.
Wonderful. Thank you so much, Terry. Yeah, it's a privilege to go after all of these great speakers and try to tie some of these things together. I'm going to be talking about what I'll call elevating the foundation of models for climate smart agriculture. And this is really thinking about how we can create kind of community public goods and maybe a process that might move us towards more kind of collaborative efforts in this broad area. I showed this slide yesterday, but I'll just recap. This is thinking about how we often are using crop models to focus on fundamental responses. Here I'm focusing on climate responses, but we could do a similar thing for carbon processes or greenhouse gas exchanges. But the idea being we can use this to understand the present day, to understand the past, and to think in long term about the future, reacting, but also being proactive as we go out forward. So the fundamental thing that I want to say here, however, is that it's the same model setup in many cases that allows us to go to all these directions. So if we can concentrate for a moment here on just getting the best possible setup, the number of applications gets very exciting, and there can be mutual benefit to that kind of collaborative effort. So we've already seen throughout the talks today and over the past several days that there are multiple perspectives that we may have on any given agricultural field. Of course, we can utilize direct observation through surveys and reports. We can use just straight up weather indices, which are still very, very widely used around the country and around the world. And of course, there's remote sensing, thinking of vegetation and soil status and other things that we know we can get there. Of course, we have a focus on crop models within AgMIP that we can look at for within plant and below ground status and processes. As was mentioned yesterday, maybe some of the most interesting outputs are those things that we can't directly measure. Then, of course, we also can use models to get beyond the observed experience to think about different management conditions and what if type questions. There's also the potential to think about nonlinear effects where one index or one rule of thumb might interact with a second index or a second rule of thumb in a way that is not additive, but really requires this type of complex analysis that a model might shed light on when we can't calculate it by hand. But the bottom line here is that there's likely to be a different blend of perspectives that give us the best overall sense of what is happening on any given field. We can't expect it all to come from any one of these sources. And in many cases, these things can connect and lead to something greater than the sum of its parts. So one of the things we've been doing in the last year or so is building up stronger collaborations between AgMIP and NASA Harvest. To think about how we can make better use of remote sensing in the general crop modeling context. And also what lessons do we get when we apply remote sensing in crop modeling that tells us about how well we're doing in the remote sensing realm. So one of the things we've laid out here is, it might seem somewhat trivial, but it's a table that looks at the various types of crop model input types that go into setting up a successful crop model application. So starting on the far left, they break down into three major categories of when you might need this information. So prior to an experiment being run or prior to a season, you might look for information around what land use is there, what management is happening on the field, what's the genotype or the cultivar information, and then what are the initial conditions as you're beginning the season. Of course, during the season, we need to know what the driving weather is. There are different types of data sets that we might look to for that. But there also is interest in various state variables within the cropping system, things like biomass, but also in the soils, soil moisture and nutrients, other things like that. And then there are also really interesting new observations that focus on specific processes, not so much a state variable, but a transfer of energy or mass or water, for example. And that includes things like ET and direct photosynthetic measurements. And of course, at the end of the season, crop modeling is not necessarily done when virtual harvest occurs. Oftentimes, we need to incorporate additional damages, as Jonas just showed. If we have information about floods, we can incorporate that before we give our final estimation of what's happening. And likewise, things like pests and diseases or the derecho that swept through Iowa. These are the types of information that we might be able to use. And then, of course, there's validation. Sometimes you want to combine an estimate of biomass or yield that came from remote sensing with what you're getting out of a crop model. So overall, when we look at this, everybody who's run a crop model has made some kind of assumption about any of these things. Maybe the assumption is, we're going to use a cropland data layer for land use, or we're going to use other publicly available sets of information, or maybe just make assumptions about the types of farm systems that are representative of a given region. But there is room to improve in any one of these areas, not only in terms of the products that might go into a crop model, but also the way that the crop models receive those products, the specific types of implementations in the model itself, or data assimilation systems, or when we get to the end of season, maybe the way we combine different sources of data to have a final set of products. And of course, this is just a sample. We know that there's others here, but trying to get an idea of this. So this is a further demonstration of some plots that Jonas introduced in his last talk. We're going to zoom in here on Iowa. This is a 30-meter resolution simulation that we've been doing with my colleague Luke Monholland, who's also somewhere in the audience. And this is a set of simulations with corn in yellow, with brighter colors being higher yields, and soy in green, same with higher colors in higher brightness being higher yields. But before we even zoom in, I just want you to note that you might see some county level outlines here. These are things where we got information on the NASS county level, but know, of course, that there isn't that stark line running across the northern part of Iowa. So even as we're going to these super fine resolutions here, you're going to notice that as we progress from year to year, there are still artifacts of the type of information that we might get as we're looking at subsets of available data. It's fun to look at this, to zoom in, and of course, with bright colors being good years, you might be looking forward to 2012 because that's going to be a dark year with a major drought, which comes up right about now. And this type of information is useful because getting down to this fine resolution is also now getting us to the resolution of remote sensing products. As Bruno showed, we can find those scaling, 30-meter down to very fine sub-meter resolutions. And as we're getting closer and closer, now you're starting to see, different field stability zones and other things like that. So this is the type of information maybe we need to build and think from the ground up in terms of the types of crop modeling we're doing so that we can ingest the latest generation of data systems. So one of the challenges in doing this is that there is a lot of time lost in what I'll call reinventing agricultural systems from a crop modeling perspective. So if you put yourself in the shoes of a new student or a newly funded project that is trying to get into this area, there are a lot of really steep upfront barriers or challenges that you have to overcome. And these require substantial resources and diverse expertise that are often too much to place on the shoulders of a small group or a single student even. So for example, AgMIP has shown that having more than one crop model makes a really big difference. But think about that. That means we're asking people to learn more than one crop model. It's a big task to learn one. Now we say there needs to be more than one. We also have to identify configuration data sets. We saw in Brad's chart that there are lots of earth information products out there. So how do we pick and choose? How do we understand the different sets of data that we might get from remote sensing or other publicly available GIS or other type products around genetics and management, et cetera? Of course, once you find one, you have to process it as well. And there's often a different set of technical challenges in big data and unit conversion and overall format conversions. And then, of course, to do the type of simulation that I just showed, you need to have access to supercomputers. So again, a different set of expertise. And then finally, as we're going downstream, and if we're trying to make our yield simulations turn into production outputs so that we can connect to value chain and supply chain managers or other stakeholders, or maybe even downstream model users in economics or water resources, there may be a different set of skills there. So this is the type of thing that is in many cases scaring away some of our best and brightest. It's very difficult to get into this realm. And it's hard to catch up to the groups that are, already doing, big group efforts on this area. So one of the things that, when we think about this, not just in terms of the expertise needed, but of course, there are some things that go beyond expertise, broader structural challenges in large scale modeling. For example, there's, in many cases, we just don't have the data or the data assimilation systems to make use of what's out there. We also have heard several times this week that the accuracy of data is a challenge. So for example, what we hear in farmer reports might not be the same as what you get in direct measurements of those fields. There's also a time lag in the availability of quality data. It might take more months to process the data and make it publicly available than the interventions that you might be testing would need to be implemented. Then, of course, there's also a big challenge of proprietary versus public data, as we saw in those SEEP surveys or in the field combine measurements. People don't always want to share that. And then there's also a general spatial incoherence of the scale in which models and data sets might exist. And we need to figure out scaling, as Jonas was showing as well. Of course, some of these issues are not really data, they're also modeling issues. So that spatial incoherence also applies to models. But then there are other things like how well do we actually resolve specific responses? We know that there are model biases there. We also know that there are some responses that we just don't respond to, even if we had good data on the driving conditions. And then in terms of models, we need to continue to build outreach to connect into water and carbon and nitrogen and livestock type models. And then finally, I'll just say we haven't really talked about it so much other than maybe a little bit on the first day of this workshop. But when we think about the future, it's not just the weather that changes. So many other scenarios and assumptions need to be thought of, not just for a given project, but for other parts of a broader modeling system. And creating scenarios and storylines that can be internally consistent across different modeling groups that might be involved in a bigger project is much more challenging than is often considered, and takes some kind of solid and organized effort. And then finally, of course, it goes without saying that having resources to do modeling and make it all useful can be a structural challenge. And in some cases, there's also a challenge between the time frame of the project and the payoffs in terms of when you might see the benefits of what you've found. So you could also think of this a little bit of the research to applications pipeline being a challenge. Okay, so those are what's out there, but I'll also have a note of confidence and optimism here, because there's an opportunity again to follow in the footsteps of the weather community. And what I mean by that is in the weather community, there are common frameworks for gridded models that go into common ensemble systems over the continental US. And I think we could do something similar in the agricultural realm. So that would help us, for example, if there were sets of curated historical input data sets designed for agricultural applications. Likewise, curated configuration information. Maybe we can't get proprietary information, but we can ask for summary statistics or summary information for some kind of representative or sentinel set of farms to represent a given area or system. We could do this with multiple models, multiple crop models, for example. Likewise, that would benefit from a set of common input and output formats, or some kind of workflow approach that would allow you to translate the weather inputs from EPIC into weather inputs for APSIM or DSAT. We've been working on that within AgMIP. Likewise, there is an opportunity to expand data assimilation. In many cases, we find that data assimilation is done as a calibration rather than a within season adjustment. And there's more that could be done, and also to assimilate more than one variable at a time. And then finally, I'm going to use a weather term here, but model output statistics is a common term within the weather community. Sometimes you hear about MOS, for example. This is what we are now seeing increasingly in things like machine learning. So for example, if we did have multiple models running a projection of a given year's production, and we also had remote sensing, and we also had some kind of weather index, it's those machine learning algorithms and other statistical approaches that combine those and add skill that could be developed. So there are really big benefits not only to establishing such a framework, but also recognizing that this lowers the barriers for contribution if we can make this an iterative improvement framework. This would also allow for stronger community engagement and benefit, because smaller resource projects could make an outsized contribution. So for example, if somebody were to come along and improve an evapotranspiration routine, rather than them having it for whatever local application, if it went into one of these models, it would suddenly be applied across many different places. Likewise, if somebody were to come along and improve the cultivars for soybean in Minnesota, you could put it into this system and all of the models would benefit from it. And you could imagine much smaller projects having a big impact. You could also add new products. So the next generation of crop models, or if a new crop model emerges, or a new remote sensing product needs to come in, there is a stable target rather than so many moving targets to connect with. The other thing, of course, is you can improve even a portion of the domain. So rather than expecting everybody to run and maintain full control over the entire country, it would allow different land grants or different experts in different parts of the country or different system experts to improve their portion, but all be contributing to a larger whole. And then, of course, there's also this effort with this model output statistics and elsewhere to further draw out the actionable signals. So to get more signal and less noise is something that we do through ensembles, but also advanced methods. And then, of course, also people could be working specifically on the outputs connecting into downstream connections and stakeholder engagement. So finally, same set of lists at the top here, but what can we use these models for? Just to recap, these are all the things that we think a similar set of models could be used for. So looking back into history to understand what's already happened and what we might have been able to do differently. We can do near real-time monitoring and seasonal forecasting. We can think about present-day risk management, adaptation, and mitigation, as well as future risk management, adaptation, mitigation, and the differences in various scenarios between those. And then, of course, overall, these models could be connected for water, energy, land, and carbon, and other greenhouse gas type resource management. And of course, all of this is why we're here, to think about climate smart agroecosystems. So that's my last slide. To put it all together, the idea here is we've seen lots of great work over the past several days. Question is, how do we tie it together, and how do we make sure we're all kind of paddling in a similar direction and start to create the structural or infrastructure that would allow us to better connect all of the great progress that we're seeing. So thank you so much. I'm happy to talk more. And I think that's the end of our session.
I think so. Well, Alex, thank you for that excellent presentation and for laying out so clearly all the wonderful explorations we can pursue and embark on to develop all of our collective efforts more effectively. We're going